Now let's talk about standard normal distributions and z-scores. So first we're going to contrast the normal distribution against this standard normal distribution. And it's going to be pretty easy because just by knowing the normal distribution, you already know the standard normal distribution. Then we're going to talk about some normal distribution problems and contrast that with standard normal distribution problems. All right. So before we talked about how the normal distribution really is a family of problems. It's not just one shape, but it could be sort of stretched or shrunk on that x-axis. And because of that, it's actually an infinite set of distributions all with different means and different standard deviations. So you could have means of 5 and standard deviation of 10. That's one normal distribution. And then another one could have a mean of 1 and a standard deviation of 2, right? So there's like an infinite number of these. They all fit the empirical rule, though. Now, because it's sort of problematic to work with like every single one of these different normal distributions, they've thought of this transformative system where you transform all normal distributions into what is called the standard normal distribution. And there, what we're doing is we're making the mean 0 and the standard deviation becomes 1. This way, we don't have to worry about the actual values, right? We don't have to worry that the mean is actually 50. We just have to know, oh, the mean is in the middle, right? And the standard deviation, by being 1, makes it just really easy for us to label this stuff, right? So in a standard normal distribution, what we've really done is we've transformed the values into z-scores, or what we call standard deviations, right? So we've normalized everything. We don't really care that the standard deviation is actually 10. We just care how many standard deviations away they are. So are you 1 standard deviation away, 2 standard deviations away? And because of that, we've changed this x-axis. Instead of actually putting the values, we're now putting the z-scores. So that's really the only difference between the normal distribution and the standard normal distribution. In the standard normal distribution, we basically ignore the values and we only use the z-scores. And we have everything in terms of standard deviation. Are you 1 standard deviation away, half a standard deviation away? That's all we really care about. So in a normal distribution, which I'll draw in blue, in a regular normal distribution, what we usually have is probability, which is the area. So this is represented by area. The raw score with the mean, median, and standard deviations and actual values, things like 550, 450, right? And we have the z-score. 0, -1, +1, right? So that's what we think of as a normal distribution, a regular normal distribution. What we do in the standard normal distribution is we basically ignore that part, right? So it's the same thing. We still have probabilities and we still have the z-scores, right? But now all our scores are z-scores. We don't have any other scores other than that. So that's really the only thing that's different about a standard normal distribution. All right, so now let's talk about the z-score, the raw score, the mean, and the standard deviation, and the relationship that they have to each other. Before, we really did it in a very sort of intuitive way. For instance, if our mean was 10, so our mean is 10, and our standard deviation is 5, right? How do we know where to draw these notches? Well, if it's a normal distribution, we know that approximately this area should be about 68%, more than half. What you could do is look for the point of inflection. Often in my drawings, the point of inflection is really hard to see, but in a nicer drawing, you could see the point of inflection. But what we could see is one standard deviation away means that it's a distance of 5, right? What would this value be right here? Well, since it's 5 on the negative side, all we have to do is subtract 5. And that's pretty intuitive, right? If we want to go another 5 steps to the left, that would be 0, right? And if we wanted to go yet another 5 steps to the left, that would be negative 5. And if we wanted to go yet another 5 steps to the left, that would be negative 10, right? And so on and so forth, right? Same thing on the positive side. If we wanted to go 5 steps to the right, that would be 15, 20, 25, 30, so on and so forth, right? On to infinity and negative infinity. Now, before we just did it in a very intuitive way, and these notches just correspond. We've drawn them so that they correspond with z-scores. This is 1 standard deviation out, 2 standard deviations out, 3 standard deviations out. But there is a systematic relationship that we could exploit here and turn into a formula between the z-score, the raw score, the mean, and the standard deviation. If we wanted to go 2 standard deviations out and find what this value was, in order to find it, in order to find the raw score, what we do is take the mean and then add the z-score multiplied by the standard deviation. And this actually works for on the negative side too, because when we have a z-score of -1, then you would subtract the standard deviation instead of adding to the mean. So this formula ends up being really good for us. Instead of raw score, we usually call the raw score the x's. And instead of writing out mean, we would write mu. And then we could keep z and write sigma as our standard deviation. So now we see a formula here that allows us to go from the mean, the z-score, and the standard deviation into a raw score. Now, we could use this formula to find anything, any of those 4 things now. If we wanted to find the z-score, for instance, and we did some algebra to this, we would just see that that's actually the distance between the raw score and the mean divided by the standard deviation. And let's think for a second about what that means. That means the z-score is take this distance and then cut it up into these chunks. How many of those chunks do you have, right? So the z-score really is telling you how many standard deviations are you away from the mean, right? So it's totally relative to the mean and standard deviation. Also, you could use this very same formula to solve for the mean and standard deviation, right? So we could do that over here, right? So let's say we wanted to solve for the mean. What would that look like? Well, all we would have to do is move this over. So that would be x minus the z-score multiplied by the standard deviation. And then let's say we wanted to find standard deviation. What would we do then? Well, that's pretty easy as well. All we have to do is you could just take this formula and swap these guys. And so that would be standard deviation equals x divided by z. Right? So here we see that using this very simple formula, and you could just remember one of these because having one of them, you could derive the other ones from it. Just by having one of these formulas, if you had any 3 of these, you could solve for the 4th one, right? And you don't even have to do the algebraic transformations. You could just plug them in and find what's missing. Yeah. All right. So far, we've only talked about z-scores where it's nice and even, like 1, -1, 2, -2, right? But we haven't talked about weird z-scores. For instance, what about a z-score of something like 0.5, right? What would be the area over here? Well, some of you may be tempted to take 34%, 0.34, and divide it in half. But as you'll see from this picture, that won't quite work. You're not really dividing this area in half, right? This area still ends up being slightly bigger because it's slightly taller than this area, and this area has this big chunk cut out of it, right? So, so you can't just divide it by half. That's not going to be a good strategy, right? That's not going to give you the right area. So how do we deal with this? Well, there's two ways of dealing with these weird z-scores and how to go from these weird z-scores to probabilities that we don't know yet, right? That are not nice and even, like 34, 13 and a half, you know. Okay, so there's two ways of doing it. One way is by looking it up in a table. Often there are tables in the back of your textbook or even in the back of an AP Statistics, like Princeton Review book or something, that show you the transformations from weird z-scores like 0.5 and 0.67 and 1.9, right, to probabilities. So that's one way of doing it, using z-tables. Z-tables. The second way of doing it is by using Excel or your calculator. If you have a fancy TI something calculator, it should also come with similar functions to Excel. And so I'm going to show you those two methods of how to go from weird z-scores to probabilities at those z-scores and vice versa. How to go from the probabilities, like weird probabilities, like 50%, we don't know where, or like 51%, right? Like we don't know what this value would be for 51%. How to go from those weird probabilities into the weird z-scores. All right, so first let's talk about the method by using the tables in the back of your book. Usually it's the first table you see back there, table A or something like that. And let's break it down. A lot of tables look somewhat like this one. Yours might look slightly different, but probably roughly similar. What it shows you up here is exactly what probability is plotted down here. What it shows you is the probability that's shown sort of on the negative side. So everything below the z-score, right? So, and this is what we call the cumulative probability because you're accumulating it as we go right? So it's adding up all the probabilities on this side. So this is showing you the cumulative probability at the z-score. Now, the table entry for z is the probability lying below z. So here are the z-scores, and these are the probabilities. Now, for the weird z-scores, what would really be helpful is if we had z-scores for, we had the z-score of negative 0.34, negative 0.341, negative 3.42, negative 3.43, right? So we had all of these decimal places, right? So it would be really nice if we had all these different z-scores. But that would be a really, really skinny list, right? A skinny list of a whole bunch of z-scores, and then a skinny list of a whole bunch of different probabilities. Now, that would be a very, very inefficient use of space. So what a lot of tables do is they put the z-score up to, like here, it's up to the tens place on this side, and then they put the hundreds place on this sort of dimension, right? So in order to find the probability for the z-score negative 3.45, right, you have to find negative 3.4 and then go to 0.05. So it's sort of like you add this, you sort of stick that on there, right? If you added it, it technically wouldn't work because it's negative. But pretend this is negative 2. So here, that would be negative 3.45, right? And at negative 3.45, the cumulative probability is 0.05. 0.0003. Notice that it's a very, very small probability. It's not 0, but it's very, very small. So let's do another example. Let's say we wanted to know the probability at the z-score negative 2.48. So we'd go to negative 2.4 and then also go to 8, and that would be our probability, 0.0067, less than 0.01, right? Less than 1%. Now, what if we wanted to find out the upper side, right? Like we're like, oh, you're only giving me the cumulative probability on the lower side. What if we wanted to find out this probability at positive 2.48, right? What would we do then? Well, because the normal distribution and the standard normal distribution to boot is perfectly symmetrical, what we would see is that if we know it for the negative side, we could just flip it over on the positive side. So if the negative side over here at negative 2.48 is a probability of 0.0066, then this too is also 0.0066 because it's perfectly symmetrical. So you don't really need to have both the positive and negative sides. Oftentimes, tables might just give you the positive side or just the negative side. Sometimes they'll give you both, but you don't actually need both. You could just figure it out from there. All right.